or really it's chapter 2.1 and a little bit of 2.2 corresponding to the short homework that I'm going to assign toward the end of break, which will be due at the end of the next week back. I just want to remind you that I'd asked you to read section 2.1, which is about matrix operations. A huge portion of that section is examples of matrix multiplication and various interpretations of matrix multiplication. And I just want to point out the fact that we've already covered matrix multiplication in terms of the mechanics of doing so. And we certainly know how to multiply a matrix times a vector. So I'll just give you a couple of reminders here about how that works, and just reminders about matrices in general. A matrix is an array. It has entries. We typically say m by n. M corresponds to the number of rows, and n corresponds to the number of columns. And so when you're talking about the entries, you can tag each entry with two indices. The I index goes with this m here, and it tells you which row you are in. Right? I goes between 1 and m, and it tells you which row you are in between 1 and m, and there are m rows. This j index tells you which column you are in, and again, j goes between 1 and n. These are natural numbers, whole numbers. And so if you want to describe all the entries in the matrix, you can do so just with the two coordinates. And you can kind of think of them as x and y coordinates the way you would for points or vectors in the plane. But here what we mean is that the array, if it's m by m, then it has m times n entries, and you'd like to know what entry goes where, and this notation takes care of that. Now, of course, we can write it in terms of columns and rows. We haven't really internalized the idea of row vectors beyond what I introduced in the first part of class. Column vectors are actually proper proper vectors. So if you take this matrix, which is made up of all of its entries, and you slice it into columns, those columns correspond to vectors the way we understand them. Namely, the first column, C sub 1, is a vector in Rn if you just ignore the rest of the matrix. Now rows, the reason why we can't do that is we haven't really interpreted row vectors, so I'm not using the arrow notation here because I'm specifically saving that to mean vectors as we understand them, which are organized as columns. But visually you can think of this as rows, and the reason why that's useful is because the sort of practical way to do matrix multiplication involves picking up rows and multiplying them times columns using the dot product. And so it's useful to have this notation. So rows can be indicated this way. And really these are vectors as well. They're just 1 by n vectors rather than m by 1 vectors, right? So here these are m by 1. Okay, 1 means, so again, rows and columns. So there are m rows, meaning m vertical entries, and only 1 column because they're column vectors. Here, these are 1 by n matrices, which could be interpreted as row vectors because each row is exactly 1 row, but it has n entries and columns. Okay, so then just some other terminology. Here, the diagonal entries of a matrix are the AII entries. Just means where the two indices are equal. So that'd be the A11, the A22, A33, so on, as far as they're defined. And literally, if you have a square matrix, you can draw those entries along the diagonal. If you have a non-square matrix, you still have a diagonal, right? This is the 1, 1 entry, first row, first column. This is the 2, 2 entry, second row, second column. But you have other off-diagonal entries as well. Those are all of the entries which are not on the diagonal. And so a diagonal matrix is a matrix which is 0 off the diagonal or on the off diagonal. The identity matrix, which we've introduced, this is the n by n identity, n rows, n columns, has 1s on the II entries, so 1s along the diagonal, and is 0 above and below the diagonal. The 2 by 2 identity, for instance, looks like this, so you have 1s on the diagonal, 0s on the off diagonal. Okay, so just talking about the identity because we will use that matrix often. So it is a diagonal matrix because its only entries are on the diagonal. Now, of course, you can have zeros on the diagonal and still be a diagonal matrix. To characterize a diagonal matrix, what we're really interested in is whether or not the off-diagonal entries are all 0. But the other property of this n by n identity matrix is that it is square. So henceforth, we're going to refer to square matrices as matrices that have the same number of rows as columns. And this will turn out to matter when we talk about unique solvability and matrix inverses. So the zero matrix, as an example, is a fun one. That's the matrix that has zeros everywhere. It's a fun matrix because it is the additive identity. When you add the zero matrix to another matrix of the same size, it doesn't modify it because, as we will find out in the next little bit here, we add matrices term by term in the same way that we add vectors term by term. And also in the same way that we can only add vectors if they have the same length or dimension, we can only add matrices if they have the same size. Namely, they have to have the same number of rows as columns. So this is square matrix. These are non-square matrices, right? So this is a row vector. So this is 1 row by 4 columns, a 1 by 4 matrix. And then this is, let's see, 2 rows by 3 columns, 2 by 3 matrix. And these are, of course, not square because they have more rows, they have more columns than rows. Okay, so I didn't cover matrix arithmetic, which is Theorem 1 in section 2.1, because these are things which are, at this point, you've used them and they're more or less obvious, but they do require a proof. And involves the definition of matrices and their sort of underlying axiomatic properties. Not terribly enthralling, but I just wanted to highlight some of the big things. So matrix arithmetic, first of all, you're only allowed to add or combine matrices of the same size. Now, we're not talking about matrix multiplication, we're talking about addition and subtraction. So first of all, if you're going to add or subtract matrices, they need to be of the same size. Component-wise addition, so addition and subtraction are always done component-wise in the same way that vectors are, and that addition is both associative and commutative. Now, this can get confusing because matrix multiplication is associative, but it is not commutative, whereas matrix addition is commutative, meaning the order in which you do the addition, A plus B, or B plus A, they will always be the same. But as we'll find out below, for a variety of reasons, A times B through matrix multiplication is not necessarily equal to B times A. You can multiply matrices by scalars, and to do that, you simply multiply each component by that scalar, and you can always add the zero matrix, for instance this, to another matrix as long as it's the same size. And this property, as I said before, is the property that the zero matrix is the additive identity. When you add it to a matrix, you just get the matrix back out. Hence, it's the identity with respect to this operation. Now, I did not go into detail about the mechanics of matrix multiplication or the interpretation in terms of rows and columns, because as I mentioned, we've done that before. And also, since I actually asked you to read this section, there are some really good graphics and visualizations and several examples of matrix multiplication. So if you're struggling with that, dig into this section in section 2.1, subsection really. But I'll just remind you some of the basics here. So if you have two matrices of different dimension, so if A is an M by N matrix and B is an N by P matrix, then they fit together A times B. And what happens is you check to see that these two agree. In this case they do, which means I can set A to the left of B because N is equal to N. And then when I do that, the N's collapse and the resulting matrix will be M by P. And so we'll talk about why that is. Now notice, AB and BA are not even necessarily defined. So AB here is defined because these N's match, but if I wanted to multiply B times A, notice that P is not necessarily equal to M, so it is not obviously legal that I can set B to the left of A. So that's the first indicator that matrix multiplication is not commutative, because it is not necessarily the case, even if AB is defined, that BA would even be defined. So that's the first thing to note here, and I'll say this again in a few minutes. Okay, so how do we interpret matrix multiplication? Well, it's actually through a composition of linear transformations. Now, if that sounds scary or you don't like it, what we can do is we can actually just think of sort of order of operations. So if I want to do A times B times X, where X is a vector, I can do this in several ways. So the first thing is, as long as the dimensions match, so if X is a vector that B can multiply, so for instance, if X is, let's see, what was B? B was N by P. So if X is P by 1, then B can act on X. So you do this matrix multiplication, and afterwards, if B is N by P and X is P by 1, then the resulting object, which is BX, will be an N by 1 vector, right? N by 1 vector, and that is precisely the type of object that A can act on, because A has an N here, and so that's what we mean by this. So this would be take B, multiply by X, that results in an N by 1 vector. Those are the types of vectors that A can act on, and so then you act on it. I don't know why I wrote it like this, that's just redundant. Really what this should have been is it should have been A times B times x. And the way you would see that, I apologize here, is that if A is m by n and B is n by p, then their product is m by p. And if it's m by p, then that matrix can act on a p by 1 vector, which would result in an m by 1 vector. So these three things are equal, noting that I have a little typo here. This should be A times B first, then multiply on the left by x. So I mentioned composition of linear transformations. Well, we know from the last week of classes, last 2 weeks, that each matrix represents a linear transformation. So if A is an m by n matrix, then it represents a linear transformation from Rn to Rm. So I'm just writing out the dimension here. Just make sure you don't forget that the order swaps. This is the dimension of the matrix, and this is what it does in terms of a linear transformation. So if B is n by p, then B goes from Rp to Rn. And if x is an element of Rp, then what we have here is exactly what I mentioned in the previous slide, or previous discussion, which is that if x is in Rp, then B is allowed to act on it. So what are we really thinking? What we're thinking of is exactly this. So this is an Rp, so B acting on it is an Rn. That's Bx is an Rn, and A can act on things in Rn, and it produces things in Rm. So that's just matching up the dimensions. And so how is this a composition? Well, if you start in Rp with a vector x, then the matrix B, which acts first on it, will land you in Rn. Once you are in Rn with the vector Bx, there should be a hat here, then A can act on that, and when A acts on anything in Rn, it takes it to Rm. And so you start with a vector, B takes that vector to Rn, and then the resulting vector Bx gets acted on by A, and that lands you in Rm. And the way we visualize that is the matrix product A times B. And so by composing two linear transformations, we get a new one. And so again, if you're thinking about a mantra here, the composition of two linear transformations, each represented by matrix A and B, results in a new matrix, A times B, using matrix multiplication, and that itself is a linear transformation from Rp to Rm. This is what's called composition of maps. So you have two maps, you compose them to create a new map, and then that map has the name AB, which is convenient because if the linear transformation represented by A is this, linear transformation represented by B does this, then the new linear transformation from Rp to Rm is just the product of those two matrices. So that's a cool fact. So I'm encouraging you here to do some examples with matrix multiplication, and make sure you read about the matrix products in terms of their interpretation in terms of rows and columns.